before we move on. So what is an algorithm? An algorithm is a specific set of steps to find a solution to a specific type of problem. What is evolution? Evolution is a natural process which acts on a population of organisms. Hereditary information is passed from one generation to the next in the organism's genome, its DNA, its chromosomes. Mutation and crossover, or mating, add random variation to the genomes in the population. So they add randomness to the population. And natural selection removes organisms whose genetic code is less fit to their environment. And with each passing generation, because of natural selection, the organisms in the population better suited to their environment survive, procreate, and presumably the population overall becomes better suited to its environment. And you'll notice that I've bolded some words here. I tried to bold them as much as possible through the rest of the presentation because it'll help you see the analogy between actual evolution and genetic algorithms that try to mimic it. So genetic algorithms, in the most general sense, are what are called stochastic global optimizers. And that's a lot of long words, basically to say that genetic algorithms look for the best solution that they can find, that there's a random component of the algorithm, so obviously it won't run the same way twice, and it finds better solutions with each iteration, but it may never find the best solution, even if you run the program forever. And I'm going to use specifically an example problem here to sort of guide you guys along with a little more practical example. So I'm going to use this problem, the problem of maximizing the number of ones in a binary string of length 10. It sounds like a very simple problem, but it's probably best to start simple. So whenever you're trying to solve a problem with a genetic algorithm, you have to have two things. And these two things are tailored for that specific problem. You have to, and this involves some creativity. You need a representation that is what solutions to your problem look like, how you're going to represent them. It's genome, if you will. The other thing that you need is a fitness function. This is an equation that operates on a solution and tells you how good or bad that solution is. So in our example, we might use as our representation a 10-digit binary string. I've chosen that. I could choose other things as well, like hexadecimal numbers or something. But here we will use a 10-digit binary string. Our fitness function will be the number of ones in the string. I could, again, choose something else. It could be, I want to, rather than maximizing the number of ones, I could try to minimize the number of zeros. So genetic algorithms, to outline them broadly, I'll go into each one of these steps on their own in subsequent slides. The genetic algorithms work like this. We start out with a population of random solutions, completely random. We calculate each solution's fitness. We select solutions with the highest fitness, mate the fittest solutions more than the unfit solutions, and then slightly mutate the offspring. Once we're finished with that, we've created a new population, which we call the next generation, and we go back to step 2 and repeat this process and iterate basically until we want to stop. So step 1, the initial population. We start out with a population of solution genomes in our chosen representation. And I will be your sort of Steve Irwin or Jacques Cousteau here, telling you about this population of 4 strings, these 4 organisms, binary strings. So I chose arbitrarily 4, a population size of 4. There are 4 binary strings here. I chose them randomly, I created them randomly, so we will follow their life cycle. First, we calculate the fitness function for each member of the population's genome. So in our example, we simply go through each binary string and count the number of ones in the string. Step 3, selection. We find out which solutions are the fittest and ignore the rest in our case. So the genomes having fitness of 3 and 7 are the fittest. Another way you might think of this is these guys are the strongest members of the population, or the sexiest members of the population. They're going to have the most offspring. So there they are, the ones with 7 ones and 3 ones. And I warn you, this is a little graphic. We have binary string sex here, so don't freak out on me. So we're going to, in the crossover step, create offspring genomes by randomly swapping their parents' genomes at a random point. So this is the crossover operator. In this case, it's just very simple. We choose a random location. So in this case, we chose randomly 3. And all we do is flip. So one half comes from one parent, the other half from the other parent, and vice versa. So now we have 2 new offspring. Our population size was 4, remember, so we need 2 more to round out the population. So we repeat the process, this time at location 6. If we continue doing this, unfortunately, it seems really nice because we're always taking the best, but eventually we're going to converge to just a few that are all basically identical in our population. The problem of inbreeding comes in here. So you have to maintain variation, randomness, and that's what mutation does for us. It injects more variation into the population by randomly flipping a bit with a certain low probability. Now, all of these steps in a genetic algorithm have parameters basically you can set. You have lots of options, so there's no hard process for creating a genetic algorithm. It's kind of an art. You have to tweak parameters and see how you do. So in our example, we flip bits at random in the offspring that we generated, and now we have a new population. Step 5, go to the beginning, repeat. Our population has all grown up, and now they're just like their parents. We calculate their fitness and move on from there. If you notice, the population's fitness overall went up. This conforms to our intuition. You know, genetic algorithms are optimizing. They're trying to find a better solution. So I told you there were certain parameters for each one of these. One of the things that you have to sort of find a balance between, strike a balance between, is mutation and crossover rates. The goal, or what you're striking a balance between, is preserving existing information and generating new information. Crossover preserves information in the population, but mutation generates new information. It's generating new information at the cost of destroying what you've already learned. So a high mutation rate and low crossover would correspond to an aggressive global search of this, almost brute force search, if you will. A low mutation rate is less aggressive. You're exploring a very small area of your search space. So I told you that there were 2 things that we need anytime we want to use a genetic algorithm for a specific problem. We need a representation. So in the problem that we're trying to solve here, the input crafting problem, we need to decide what inputs we're going to inject. How are we going to describe them? The other thing is we need a fitness function. That is, how are we going to measure how good an input is? So our representation, we need to inject input in a certain format. We don't just want to throw binary strings in arbitrarily, because that is a very, very huge search space. So our representation describes the steps used to build the string, rather than the actual string itself. We're not operating on the string itself. We're operating all of the crossover and things like that, or operating on a specific set of steps to create the string that ultimately we input into the program. So to do this, the rule set that we use is a context-free grammar. This is a grammar for, grammars are a way of describing languages. We all know that sort of intuitively. Context-free grammars are a formal grammar, which means that it's mathematically precise. Context-free grammars consist of terminals, which are ultimately the things that are actually in your language. If we were talking about terminals in English, we would be talking about words, everything that I've said in the whole presentation, etc. Non-terminals are placeholders, sort of like variables in algebra. If we were writing a grammar for English, again, we would talk about nouns and verbs, adjectives. Then we have production rules, which are substitutions that you're allowed to make for each non-terminal. So, for example, in a noun, you could substitute a specific noun: man, dog, cat, computer. The initial rule is the first production rule. It's just a production rule like all of the rest, but you start from there. The process of generating a string begins at the initial rule and proceeds until there are no more non-terminals in the string, no more noun and verb. We actually have a specific sentence, the man ran. So this is an example in sort of the standard textbook format way of writing grammars. So normally you write terminals in lowercase letters. So lowercase c, lowercase d, lowercase e, lowercase s, lowercase x. These are all the things that are actually in the language that this grammar is trying to describe. The rest are just variables. These guys are written in capital letters. Again, this is just tradition. So the non-terminals in this case are bold capital letters. Each one of these on the left is a production rule or a substitution rule. And this means if you see this non-terminal in a string, you can substitute it for any of the rules that are to its right. And again, by tradition, normally S corresponds to the initial rule, and that's where you start. So I'll try and make this, again, a little more explicit by giving you an example. So we start out with our starting rule. We can substitute for S either S, capital A, lowercase s, or lowercase x, capital B, x, or a lowercase m. So I will just choose one arbitrarily. We choose x, b, x. For the b in that, because it's a non-terminal, we can substitute again any of the things to the right of b. So we have three options there. We substitute again the first, and we repeat this process again now, substituting for the a. Now we'll substitute for the b. And finally, for the c, we substitute one of the three and end up with all lowercase letters, or all terminals in this case, which means we're done. We've created a string in the language that this grammar describes. So a grammar is a description of how to build all possible input strings, not a specific one. It's a description of a whole language. GA operators are not good, or GA operators are good for integer strings, but not like operators, not rule sets. This is, I described to you that we're dealing with binary strings or integer strings. In that example that I used, the binary strings. How would you do that on a rule set? That doesn't even make sense, really, does it? So how do we use a grammar to build a string that's actually in this language specified by this grammar? Or for a very specific example, how do we turn the integer string 10247 into that specific set of all terminals? And we're guaranteed that it is actually in this language described by the grammar. So we use a process called grammatical evolution. So to produce a string from our grammar using a series of integers, we use grammatical evolution, which can be summarized in the pseudocode. So while there are non-terminals in the string, just like before, we don't stop until it's all terminals. We find the first non-terminal from the left in the string. So we'll define num rules here just to have an abbreviation. It's the number of production rules for that first non-terminal. So if it was A in the previous slide, I think it had 2 production rules. Just a simple number, just an integer. So we take whatever the next integer is in our genome. We just go down from left to right, our genome. And if it's a 1, 2, 3, we just mod by the number of rules and apply that production rule. So again, I'll give you a specific example. So we start off as first we number